podcast. This is Mr. White.
And Mr. Sadler.
And it is the holiday season.
Yeah.
So I'm such a giving guy. We're going to go ahead and do the AP Plus for Section 3.
All right?
So do you think anybody will say thank you?
No.
No, they should, though.
They should.
They should. So we're on page 378 of your book. It says you can use algebra to find out how high the pop-up toy should go. So go ahead and help me out, Mr. Sadler. Read instruction 1 for me.
Okay, it says when the spring is completely compressed, but before the toy has popped, what is the kinetic energy of the toy? I know that one.
Okay. So it's not moving?
It's not moving, so the kinetic energy is probably 0.
Yeah.
What is the equation for the toy's spring potential energy?
Okay. So we just covered this in the last podcast. And so off to the side here, you knew that the kinetic energy was 0 because,
The object is at rest.
and since the kinetic energy equation is half mv squared, 0 squared is still 0, and
Right.
0 times anything is 0. Then there's this gravitational potential energy thing that we might need
Okay, so the gravitational potential energy before it's popped is 0 too.
because,
It's at rest, or it's at ground level, or whatever we're going
Right.
to say. It's at what we're going to call 0.
yeah, and it's not that because gravity is 0 or because it has no mass, it's because it has no height.
Correct. And then a spring potential energy, the formula is 1/2 k, which is that constant again,
Right.
times x squared,
Okay.
and x is the distance that I've compressed the spring
Sure.
or whatever.
Okay, so the spring equation there is half kx squared. That seems simple enough. So if you wanted a numeric value for that, you would have to measure how much you've compressed the spring.
Right, compared to where it's not compressed, push it down, and now it's compressed, and
Okay.
then I got the x.
And so then you'd also have to know the spring constant k.
Correct.
Okay, so we're going to leave these off to the side here.
All right.
Okay?
So we just did one, right?
I think so.
Right on. Number 2, it says, as usual, choose gravitational potential energy to be 0 when the spring is completely compressed, because that's our 0. Write an algebraic expression for the total energy equals kinetic energy plus gravitational potential plus spring potential when the spring is totally compressed but before it's popped. So we're just going to take these 3, this plus this plus this, right?
So it's got no kinetic, though,
Correct.
and no gravitational.
Correct.
So it would be the spring potential energy
Correct.
equals the total energy.
Correct.
And if I really wanted to get specific, it'd be half kx squared is equal to the total.
Correct.
That's before, right? This is the...
Right, before it's popped. After it's compressed, before it's popped.
Okay, so this is just the initial energy.
Right.
Okay,
So that's 2.
number 3 then.
Number 3 says, after the toy pops, it will shoot upward. When it gets to its highest point, what is the kinetic energy? I know that one again, too.
Yeah, so
At the highest point, okay, I've got gravitational potential, but I've got 0 kinetic energy because it's stopped moving.
so it's not moving, so it doesn't have any kinetic.
Correct.
Okay. But it does have a lot of gravitational.
Right, and then it says, what is the spring potential energy at the highest point? I got that one, too.
Okay.
0.
Right, because the spring is returned.
Totally released.
Yeah, it's returned to its original shape.
Right.
It's not compressed anymore.
Correct.
So the final energy then would be equal to the gravitational potential.
Right, because the kinetic is 0 and the spring potential is 0.
So that would be equal to the total energy. And if I wanted to get technical, it'd be mgh is the total.
Right.
Okay, so I have some initial work and I have some final. I shouldn't use the word work. I have some initial
Energy.
and I have some final energy.
So again, what we're really looking for is where are these things 0 and where are they max?
Yeah. Okay.
Okay, so now we're at 4.
Uh-huh.
Okay, so if you denote the height of the high point above the starting point as h for height, write the algebraic expression for GPE at the highest point.
Yeah, we already did that.
We already did that. It's
MGH.
just MGH.
Okay.
5, write the algebraic expression for the total energy, KE plus GPE plus SPE at the highest point. We already did that. It's just MGH.
And just to verify, it's It's just MGH because it's not moving
right?
and because the spring is no longer compressed.
Correct. Because I have no kinetic and no spring potential.
All right. And then what's it asking us to do in step 6?
It says if you assume the total energy stays the same from before popping to the high point, you may equate the expression from question 2 with the expression from question 5. Solve the resulting expression for H and show that H equals 1/2 kx squared divided by mg, where x is the original amount of the spring compression.
Okay, so well, I just said, look, energy conservation is valid. So the initial and the final are the same.
Right.
In the initial case, we have spring. In the final, we have gravitational.
Correct.
Spring energy is 1/2 kx squared. Gravitational is mgh.
Right.
I'm solving for h.
Right.
So solve for h.
Correct.
That means I got to go divide by mg. That goes away. So kx squared over 2mg is the height. That seems like a very strange, complex equation, and it is. The way to verify this, of course, is to check out the units. So the spring constant is the Newton over the meter, and mg is a kilogram meter per second squared. Okay? A Newton, if we recall, is a kilogram meter per second squared, and we divide by a meter. And what happens, of course, is stuff starts to cancel. And all of a sudden, we're left with a meter,
Which is the height.
which is the height. So it tells us that what we did was good, and everything is working.
Right on. So it shows us conservation of energy.
It shows us conservation of energy one more time. It's also important to note, and we mentioned this already in a previous pod, that when you're dealing with spring energy, mass is important. If there is no spring energy, then mass is not important.
Right,
So
it cancels.
you keep getting those questions, well, they didn't tell me the mass. You're right, but you don't need it because it cancels. With spring energy, you've got to have the mass if you're going to deal with kinetic or gravitational as it associates to spring. I believe that covers it.
Right on.
So you're welcome. And signing off, this is Mr. White.
And Mr. Sadler.